Okay, before I start with the math part, earlier we were discussing how women don't bring their families to work. Well, it's also the case here. Hi, Andrei. So, but he had a seminar today, so otherwise he would be here. So I got him online at least. So thank you for the opportunity to have a little talk about what I'm interested in. I will keep it short and as simple as I can. So yes, first I have to mention my collaborators, Kiran, Andrei, and Pavle, the best supervisor in the world. Some of you know some of them. And yeah, nobody to thank for. I'm supported by, well, Calista. Thanks, Calista. I start with complex semi-simple Lie algebra. Most of those are matrix algebras, so I will say everything in terms of matrix algebras because like 99% of the time that's what you're really thinking of. So this could be like all matrices or traceless matrices, those we are particularly interested in. So we need a Cartan involution, which is an involution that also induces some positive definite form. And the example that is usually used would be just sending a matrix to its minus conjugate transpose. And with respect to this Cartan involution, there is the Cartan decomposition. So since we are talking about an involution, the eigenvalues can be only 1 and minus 1. So, just a second. Here you are. So this first guy would be plus 1 eigenspace, and this would be minus 1 eigenspace. In terms of matrices, the first guys would be anti-Hermitian, the second guys would be Hermitian. Yeah, this, oops, I'm sorry. Okay, I said I will be short, but not that. Oops. Sorry, okay. So yeah, the weird letter covered by mouse. No, it's not. That's something. Okay, yeah, that's Gothic K. So I think the rest of the letters are easier to read. So we can take a Cartan subalgebra, but I'm not going to take any Cartan subalgebra. Those of you familiar with Lie theory know that there are many. I'm going to take the fundamental or maximally compact, which means that this Cartan decomposition gives us this one just by taking intersection with H, and this first part is Cartan subalgebra for this guy. So K is again Lie algebra, whereas P is not, but this A part is also super important, so it would be like commutative part. All right. Now, I will need something I believe not many of you are familiar with, which is a Clifford algebra, even though I'm sure you all know what an exterior algebra is, and this is quite similar, and I'm sure you've been working a lot with that. This will be some kind of a deformation. So if you take any vector space and take any bilinear form, then you can construct a Clifford algebra with respect to this bilinear form so that its generators are elements of your vector space and relations are like this, which actually makes a difference between a Clifford algebra and the exterior algebra. Because for exterior algebra, here you would have a 0. In particular, if you take B to be 0 form, then you really get exterior algebra. So I like to think of exterior algebra as a special case of a Clifford algebra. Many people think of a Clifford algebra as a deformation of exterior algebra. For me, the vector space will be, well, I wrote G or P, but I'm actually more interested in P. And B will be killing form, so it's not just any kind of a form. It's like not just bilinear, but it's also symmetric, it's non-degenerate, and invariant, which will allow me to do some nice things. Oh, already? Ah, right. I was being minimalistic. Sorry. So, for those of you that never heard about Harish-Chandra map, Harish-Chandra isomorphism, ignore this part. This is, if you know about like usual standard Harish-Chandra map, then you can make a comparison. If not, I will start as if you have no idea what I just said a minute ago. So, P can be decomposed. Well, I'm not sure if it's like proper to say triangular decomposition, but it is a triangular decomposition just restricted to P. So, positive root vectors, negative root vectors, and zero weight vectors. And this decomposition, using Poincaré-Birkhoff-Witt basis, allows us to make this kind of decomposition of the Clifford algebra. Sorry, I'm not writing which bilinear form we're using if we're using the same one all the time. So I can take like this zero weight part plus the rest. And Harish-Chandra map is just the projection to the first part. And this is not an algebra morphism, which is super easy to prove. So you see, unlike exterior algebra, Clifford algebra is simple. So it has no ideals. And every algebra map, well, it has a kernel, which is an ideal. So since A is strict, where did I go? Sorry. Since A is strictly smaller than P, then the Clifford algebra of A is strictly smaller than P. And this is definitely not a zero map. So you can't have a kernel that would be an ideal. If you want to get morphism or an algebra map, you need to at least restrict it to T invariants. T was a Cartan subalgebra of K. Now, I'm saying restricting to T invariants without explaining why that thing even makes sense. And I will do that in a moment. I'm not interested in T invariants, I want something smaller, but this is the biggest thing you can use as a domain in order to get a morphism. So, now here's the thing. If you make a commutator of K and P, you end up in P. Also, since my form is bilinear, that means that I am allowed to look at K invariants in the Clifford algebra of P, since it's a quotient of a tensor algebra. So in that sense, K invariants make sense, also T invariants make sense. And now, the theorem is that in a primary case, I believe I forgot to mention what is a symmetric pair, but since I defined Cartan involution, that pretty much settles it. But still, I apologize. Primary, it is somewhat a special case, which I will explain in a minute. So, the restriction of the Harishchandra map onto K invariants is not just a homomorphism, it's an isomorphism of algebras, meaning that K invariants also have a structure of a Clifford algebra, which is very nice. Now, if you replace letters P and K all by G, which is usually called the absolute case, then Constant has done pretty great things in that area. And, well, these kind of look smaller, but this is a generalization of his results, because this thing, primary, is something he didn't have to assume. He got it for free. If you look at the whole Lie algebra G, then you get that the adjoint representation is primary. And we had to assume that because in other cases you won't get an isomorphism of this kind. Okay, let me just say what I mean by primary. So, the formal definition of a primary representation is a representation whose every irreducible component is equal to one fixed irreducible representation. So, you just have copies of the same representation. Irreducible representation. Okay, that's nice for a definition, but it doesn't give much of an intuition. So, I wrote out some characterizations of the adjoint representation of K on P being primary. So, the first one is, first, I have to mention that when you're working with these things, you're not looking at classic G-age roots, but instead, we are using, I'm saying thank you too much. we are using so-called restricted roots. So I'm not using the whole Cartan subalgebra, just a little part of it. And what is different is that unlike the thing everyone knows about the roots, all root spaces are one-dimensional. Well, here they don't have to be anymore. But if we're talking about roots, then we can talk about Weil groups. So one thing that primary representations satisfy is that the Weil groups of K and Weil group of G are the same. Of course, in the general case, this one is larger. Also, you can say that K roots are equal to G roots or are a reduced system of roots for G. The third thing, probably easiest to explain, opposite of the equal rank case. In the equal rank case, you don't have this part because the rank of these two things is the same, so this one doesn't exist. In our case, so it's like the opposite extreme, this A is the biggest. Also, one could say that the representation is primary is if G roots are same as K roots repeated or 2 times repeated, which is kind of obvious that this one implies that once you fix your positive roots in K, then you don't have a choice for any of the roots in G. You already know which ones are positive and which ones are not. And finally, what you've been waiting for, why is that important? So, first, well, I have to promote my supervisor's latest paper. For the first one, so if you take compact simply connected groups, G and K, such that Gothic G is Lie algebra of G and Gothic K is Lie algebra of K, then the cohomology of G over K is exactly K invariance in the exterior algebra of P. Now, of course, you could say, wait, but don't you want to motivate us to look at the K invariance in the Clifford algebra, not in the exterior algebra? Yes, but as I said, those two are very close. Clifford algebra is only filtered. It's not graded. But its associated graded algebra is the exterior algebra, meaning that sometimes you don't know how to prove something in the exterior algebra. Well, you prove it in the Clifford algebra and then just apply grading. So, in order to study this one should also understand its counterpart in the Clifford algebra. Now, I'm sure even the physicists around here are familiar with the Dirac operator. Well, if I'm correct, Dirac actually was a physicist. And the Dirac operator, which we are super interested in, is an element of the universal enveloping algebra, tensor, Clifford algebra of P. And it's also K-invariant. Yeah, I'm not sure if you're familiar with the notion of this. Yes. Of the algebraic Dirac operator. So P, as I said, is not a Lie algebra, but it is a vector space. And we do have a form on it. So what we can do is take EI to be any basis of P, take Fi to be its dual basis with respect to the bilinear form, and then just look at this, where, okay, it says universal enveloping algebra of G, but P is a subset of G, meaning that these are also elements of G, therefore elements of the universal enveloping algebra of G. Also, they are in P, so we can also consider them as elements of the Clifford algebra of P. And it doesn't depend on the choice of basis, it's K-invariant and everything you need it to be. To remain a little bit on the topic of the Dirac operator, so if one wants to study cohomology of moduli space of flat connections on Riemannian G surfaces, then it is useful to also look at the Dirac operator because it is a cocycle in that cohomology. Also, Alexeyev and Meinreken were studying non-commutative equivariant cohomologies, which also uses the things I was talking about. So yeah, just to get a bit more of a promotion, you can find the paper. It's like, it really has some cool stuff. It's on arXiv, so you can look for it. And well, that's pretty much all I had to say. So yeah, in the end, I didn't need those 30 minutes at all. All right. Finally. Now I mean it. Thank you.